This is the Rode Filmmaker kit that I use for the audio for all of the videos I do for YouTube. For the last couple of videos, I've also used this optional headset adapter, and I've used yield cable lacy knot, which is from my last video, to secure the wire from the lavalier mic to the headset adapter so it works a little bit better. Now, I've been interested in adapting this to other microphones, including dynamic microphones, but the input circuitry for this isn't really completely specified in the Rode specifications, and the wiring it was not specified either. And this is a common thing I found with almost all these wireless adapters. So what we know, or what I know, is that the basic Electret condenser microphone input circuit looks like this. We have an Electret microphone here, and it drives the gate of a JFET. We assume that this drops to 0 volts, even though there's no resistor here. Over time, just the leakage currents will drop this down to 0. And the power for the JFET is supplied from the amplifiers. There's some drain voltage that it supplies and a series resistance, RD. So and at 0 volts, this FET's going to draw some current, IDSS, which is basically the drain current with the gate voltage at 0. And ideally, you want this IDSS to be VDD over 2RD. So what happens if you hook a dynamic microphone up to this Electret condenser input circuit? So here we have a dynamic mic, but now the dynamic mic is going to draw current from this supply, and it's going to be on the order of 1 or 2 milliamps, and that's going to cause the diaphragm in the dynamic microphone to offset probably far more than it would normally just from sounds. Now that may or may not be a problem depending on the design of the microphone, but it's not a real desirable situation. And the other issue you're going to have is that the output of dynamic mics tends to be slightly lower than those of an Electret mic. So this is the block diagram of the Rode Filmmaker, and they specify the input impedance is 10K, but they don't tell you what this stuff is here. And this is what we need to know to adapt another microphone to it. So the way the Rode Filmmaker works is the signal comes in, it goes through it. Okay, so this is my guess is what's going on in the Rode Filmmaker. I don't have a internal diagram of it. This is just what my guess is. It comes in through a buffer amplifier, then it goes through the switchable attenuator, and the buffer amplifier includes a low-pass filter. Then it goes into the A to D, and then it goes into a digital signal processor, which converts the now digital audio stream into the digital encoding for the RF transmitter. The RF transmitter sends an RF signal to the receiver. That receiver then feeds into a digital signal processor, which decodes the digital signal stream from that we're sending out into a digital audio stream, and that digital audio stream then goes into a D to A converter through the switch attenuator and then into a buffer amplifier and out. So if we want to know what that input circuit is, we can measure it. We unplug the microphone and we can measure the open circuit voltage here. And we do that but just by plugging a voltmeter into the microphone input of the transmitter. And so we're measuring this open circuit voltage, and we get 4.982 volts, essentially 5 volts for VDD. Now we also want to know what this RD is, but we can measure the short circuit current. So what we do is we flip over and we plug into the current input of the ohm meter or of our multimeter and switch it to the milliamp scale, and we measure the current we get. And of course I'm ignoring the input resistance of the meter, but this is close enough. Now we can take that open circuit voltage and that short circuit current, divide the two, and that will give us the value of that RDD resistor, which we get as 3.14 k ohms. And it's probably 3k because that's the closest standard value. So now we know that we have this 3k resistor here, but we don't know what the value of this capacitor is yet. And we don't know what the overall gain of this is. So let's measure it. So what I did is I hooked the RØDE Filmmaker up to my Siglant scope, and using the Bode plot mode, I measured the frequency response. So you can see here, starting at 10 hertz, it rises up, and it's fairly flat, and then it drops off. Where it's flat, I got 0.4 dB, or a gain of 1.05, which is approximately 1. So the system essentially has no gain. There's a 23 kilohertz brick wall anti-aliasing filter, and that's and then the low frequency 3 dB point I got was 29.8 hertz. Now from this low frequency 3 dB point, and knowing that the input impedance is about 10k, we can get what that capacitor is. And I calculate 0.54 microfarads. Now the closest standard value is 0.56 microfarads. So we'll call it that. So now we know that the RØDE Filmmaker looks like this. We know, and then from other measurements I made, I know that this ring is unconnected. So the input comes through the tip and the shaft. This ring part is unused. And we get 5 volts through a 3k ohm resistor. So now we know how it's powered. There's no gain through the system, and it comes out. And so now I know enough to adapt other microphones to this system. So I have this Sony dynamic microphone I've had for many years. I don't remember how long I've had this. 30, 40 years, a long time. And it's a 320 ohm microphone, and its recommended load impedance is more than 3k. And I wanted a very simple circuit to adapt this to the RØDE Filmmaker. So what I'm going to do is I'm going to do this. I'm going to take the dynamic microphone, go into the FET. This will be a jack where the microphone plugs in. I've got a 10k resistor here to keep the input of this 0 volts even when the microphone is unplugged. And this 10k is higher than the 3k the minimum they recommend. And then the output of the drain of the FET goes to the output plug, and that will plug into the Filmmaker. So what this does is this circuit prevents DC current from flowing through the microphone. The DC current from the Filmmaker just flows through the FET, just like it does with the Electret microphone. And it provides some gain, since dynamic mics tend to have lower output levels. Now I could put a parallel resistor and capacitor in here if I wanted to, but that lowers your possible swing range, and I don't really have the room in the case, which I'm going to use for additional parts. Anyway, so I dug through my box of parts, and I have a big box labeled discrete transistors, and in there I found this bag of JFETs. It's a Siliconix part. You can see the Siliconix symbol on the top of the can. It's a 2N3369. Anyway, so I went on the internet and I found this old Siliconix data book from 1986. And in 1986, this part was already obsolete, replaced with another part. So this wasn't too helpful. So then I looked some more, and National made the same 2N number. And so they have National has it by die and process. So this die is used for all these different part numbers. But if you look at the IDSS that they specify, they've got a 6-to-1 range. That's not really too helpful. I want one that's about half of the 1.6 milliamps we measured, or maybe, around 800 microamps would be ideal. So this really wasn't too helpful either. So just out of curiosity, I looked at Mouser and DigiKey, and they both sell this Toshiba transistor, which is made for condenser microphone applications. You can see down here that the parts are binned and marked by IDSS. And if I wanted to use one for this circuit, I'd use the R or the O class because their IDSS is in a range that will work. So what I did is I took the FET and tossed it on my curve tracer. Now the curve tracer puts a staircase into the gate to source gate of the FET and sweeps the drain to source voltage, and then measures the drain current. So each one of these curves is a different gate to source voltage. I have 0 to 5 volts horizontally for the drain to source voltage, and 0 to 1 milliamps vertically. The 0 volt line is the line we're interested in. VGS at equals 0 at a given VDS is IDSS. So whatever IDSS is essentially the point we pick along this line. Now now we're going to do a DC solution for the bias point. So this is the same set of IV curves, but now instead of going from 0 to 1 milliamp, I'm going from 0 to 2 milliamps. So first we mark the short circuit current we got of 1.58 mA, which is right here. And then we draw a line from this short circuit current, which is at 0 volts, to the open circuit voltage, which was 5 volts. And the slope of this line is -1 over the resistance we calculated. Where this line intersects the VGS0 line is where the part's going to bias up. So it should bias up at about 670 microamps and 2.8 volts. So remember this 2.8 volts. Now this point where the part's going to sit, this is called the quiescent point or Q point, and this line we drew is called a DC load line. So I have this external antenna adapter for an old shortwave receiver I had many years ago. I don't remember what happened to the radio. I haven't had it for years, but this has been in my part stock forever, and this seemed like a good time to use it. We know now that we could use a mono plug going into the RØDE because it only uses the tip and the shaft for the input. So inside here, I built that circuit. You can see here's the JFET, the 10K resistor. You can't see, it's hiding underneath. Here's the input jack, and this is the wire going to the output plug. So now I plugged it into the RØDE, and I'm measuring the voltage I get across it. Remember from the graphical solution, I predicted 2.8. I got 2.7. That's pretty good considering I was doing a graphical solution. I'd say that's a success. So now let's look at the IV curves again. We can do some measurements here, where again, this is the Q point. We can look at the change of voltage going in and compute the change of voltage going out from this IV curve. And we get a voltage gain of 14.5 dB. But this isn't really the right gain, but I'm computing this. You'll see why I'm doing this later, because this ignores the 10K input impedance of the RØDE transmitter. So what we really need to do is do a more thorough calculation and consider everything. So first we're going to measure GM. GM is again the change in drain current over the change in gate to source voltage at some fixed drain to source voltage. And that drain to source voltage we're going to pick is our Q point, because that's where the part's going to sit. So the Q point is right here. And we get a GM of 1.66 millisiemens. Now we also have to consider the slope of this load line and the output slope of the IV curve. So we have this 1.36K, then we have the 55 K ohms and I'm estimating that from the slope of the IV curve at the Q point. And so we can calculate the gain now as GM-RL, where this is GM, and RL is the 3.16K in parallel with the 55K, in parallel with the 10K, which is the input impedance of the preamp. We get 3.66, about 11.6 dB. So what's going to happen in the really for the load line is when the part's operating, it will go to this the DC load line will give us this part, but when it's amplifying, it will move up and down this AC load line or dynamic load line, not the DC load line, where the slope of this load line is determined by the parallel combination of all three of those resistances. Anyway, so let's do some measurements. So here's the measurement of the gain of the Filmmaker by itself without the preamp. Now we add the measurement of the preamp plus the Filmmaker. Now we can get the gain of the preamp by just taking the difference of these two curves. So we can see here, I got 11.1 dB for the gain. I predicted 11.6. I'm half a dB low. But, you know, I was just kind of eyeballing those slopes. So that's not a bad calculation. And the 3 dB point has moved down a little bit, which we expect, because here the 10K is in parallel with 50 ohms, and here it's in series with 50 ohms, and here it's in series with about 3K. But what's interesting is we see that the gain of this preamp is rising at low frequencies, and now I'm going to explain why that happens. So here I did a simple LT SPICE simulation, where here this is represents the generator I'm using for the measurement. This outer dotted box is the little preamp I built. Here's the 10K resistor. The inner dotted box represents the JFET. R0 is its output resistance, the slope of that line. This is the resistor that supplies the DC power, or 3.16K. And then we've got a capacitor that goes to the input impedance of the RØDE link, which is this 10K ohm. Now notice here that I used a negative sign for the transconductance, and that's because normally when you draw a FET, the arrow points the other way, but the transconductance symbol in LT SPICE has the arrow pointed up. So I just used a negative sign. So if we look now at the response of this at the output, so we're looking here at the output, we measured from here 10 hertz up to 100 kilohertz. I don't have the low frequency roll off, or the brick wall filter, the high frequency fall off, because I'm not modeling it, but we're getting the low frequency roll off pretty close to what we measured. But now let's look here at the preamp output. We can see here that in our passband we get one gain, but if we go down in frequency, it will come up to a different gain. Now it looks more dramatic here, but that's because the scale is different. But what's going on is at very low frequencies, this capacitor essentially disconnects this resistor, so we just have these two resistors operating as the load. And remember, we calculated like 14.5 dB, and we're getting here 13.9. So we were close. So that's why I did that other calculation, to show you what's going on at low frequencies. And then as we come up into the passband, this one's in parallel now, and so the gain drops, and this is what we got. And it's actually expected. So the key question is, what does this thing sound like? I'm using the Rode lavalier mic that came with the Filmmaker kit on the headset adapter, and this is how I've recorded all the audio on this video up till now. Now I'm going to mute the transmitter here and hook up the preamp I made along with the Sony dynamic mic so you can see how that sounds.
Okay, now I'm using the Sony dynamic microphone, and it actually sounds okay. Not great. I mean, it's a very inexpensive mic from the 1970s, but it works just fine. Anyway, if you liked this video, please give it a thumbs up. And if you'd like to see more videos from me, please subscribe. Thank you for watching.